Okay, so what we want to look at here is some combustion analysis. Usually these questions are presented to you much the way this one is up here, which they'll give you some sort of unknown hydrocarbon, or they'll tell you the hydrocarbon, but they won't let you know what the formula is, and then they'll provide you with a molar mass and some data of some of the products. A combustion reaction is when we have a hydrocarbon, so a hydrocarbon CXHY, and the CXHY, what we're using this for, the X here and the Y, is we're basically saying that we don't know what X and Y are, but through this process we're going to try to figure out what X and Y are. So it's a hydrocarbon, and since it's combustion, it is plus oxygen gas, and the two products are CO2 and water, H2O. Carbon dioxide and water. So, and our question here provides us with some data. It says our hydrocarbon, when combusted, produces 30.28 grams of CO2 and 15.50 grams of water. So, what are we going to do? How are we going to solve this problem? Well, the way that we do this is we need to figure out, if we're going to solve for the empirical and the molecular formula, we need to get moles of carbon and we need to get moles of hydrogen so that we can get a ratio and from there solve for our empirical and our molecular formula. So the way this little trick works with combustion analysis is that you'll notice all of the carbon in the hydrocarbon ends up as carbon in the CO2, and all of the hydrogen in the hydrocarbon ends up as hydrogen in water. And so we can manipulate that. We can go from 30.28 grams of CO2 to a number of moles of carbon, and we can go from 15.50 grams of water to a number of moles of hydrogen. And once we have those two, we're ready to go. So let's show you how we do this. So we're going to calculate these here. We're going to put some calculations down here in two lines. And in the first line, we're going to do the calculations for carbon. And in the second line here, we're going to do the calculations for hydrogen. So let's pick a different color here and start working on it. So we're given 30.28 grams of carbon dioxide, CO2. And the first thing that we want to do is we want to convert to moles. Oftentimes in chemistry, if you want to convert anything, you almost always have to go to moles. And so for us to be able to get to moles of just carbon, we need to first convert to moles of carbon dioxide. And so for that, we're going to need a molar mass of carbon dioxide. So we want to know how many grams of carbon dioxide are in a mole of carbon dioxide. So we're just going to scroll over here to the periodic table, and we're going to find the molar masses, and we'll calculate that. So we'll see here that the molar mass of a carbon is 12.01 when rounded to the hundredths place, and that an oxygen, when rounded to the hundredths place, comes out to 16. And we have two of them, so 2 times the molar mass of oxygen, which is 16. And our total is 44.01 grams per mole. And because we're going to be doing lots of calculations with CO2 and water, it's oftentimes advisable to memorize the molar mass of CO2 and water because they're really common and it'll really save us some time in the future. So let's drag this back over here where we can see our problem. And we're going to put that value in here. We have 44.01 grams per mole. Now, the denominator and the numerator's unit will cancel, and we have moles of CO2. And here's where we're going to go from moles of CO2 to moles of just carbon. So here's how we do it. We have 1 mole of CO2 contains 1 mole of carbon. Now, some people accept that and they get it and it makes a lot of sense, and then other students don't think that that's very intuitive. And so kind of the way I like to kind of make sense of this is I basically ask, if we had a dozen people, if we were to draw 12 people on here, how many noses would we have? And if we had a dozen people, we would have 1 dozen noses, because there is 1 nose on 1 person. And so for here, we have 1 carbon in CO2. And so if we have 1 mole of carbon dioxide, then we will have 1 mole of carbon. And so we're able to convert from moles of carbon dioxide to moles of carbon. So we're ready to calculate. Let's pull our calculator up. And we have, we're going to have to move it out of the way so that we can see what we want to calculate here. Ooh, I'm running out of space. Okay, put it right there. So we have, where'd it go? Oh, got to turn it on. You got to turn your calculator on. 30.28 divided by, so if you look over here, 30.28 is in the numerator, and we're going to divide by the denominator. 44, oops, one too many, 4.01, and that comes out to 0.6880. We're just going to keep the first 4 digits. We're not quite to the end of the problem yet, so we don't want to round to in general. So we'll keep a bunch of digits here. We'll keep the first 4, 0.6880. So our answer here, let's go back to our pen, is 0.6880, and that is, we're running out of space here, moles of carbon. So we're going to do the same thing down here for water. We have 15.50 grams of water. And we want to go from grams of water to moles of hydrogen. So our first step, much like with CO2, is to go from grams of water to moles of water. In 1 mole of water, there is a certain number of grams. So we are going to have to go back over to our periodic table and use it to calculate. So let's get rid of our previous work here. We've got what we need for CO2. And now we're going to calculate the molar mass of water. And so water is H2O. There are 2 hydrogens, and each hydrogen, when rounded to the hundreds place, has a molar mass of 1.01. And there is 1 oxygen. And when rounded to the hundreds place, that comes out to 16. For a grand total of 18.02 grams per mole. Now, I don't bring up the calculator to do this because I really encourage people to do simple math in their head, come up with ways to get this done in your head, because I really think that helps our math skills. So I'm not going to bring up the calculator for simple addition and multiplication like this. We're going to do this one in our head. If you'd like to, you can always pause the video and put it into the calculator and see that we get 18.02 grams per mole. So we're going to come back over here to our problem, and we'll be able to put in 18.02 grams per right here, 1 mole. Okay, now, almost done. Last step is we need to convert from moles of water, 1 mole of water, to moles of hydrogen. Moles of hydrogen. Now, in this case, how many hydrogens are there per water? We can see that there are 2 hydrogens per 1 molecule of water. And so 1 mole of water contains 2 moles of hydrogen. Again, going back to the analogy with people, think of it this way. If we had 1 dozen people, we would have 2 dozen legs, because each person has 2 legs. So each molecule of water has 2 hydrogens, so 1 mole of water contains 2 moles of the element hydrogen. So now we're ready to pull up our calculator and do a little bit of math here. Ooh, don't want to pull it out of the screen there. So let's clear out what we have. So we have 15.50 divided by 18.02. Okay, and we're not going to round that. Let's just leave that in the calculator and then do this last calculation. This 2 in the numerator tells us that we need to multiply that final answer by 2. And we get 1.720. And so we're going to keep a couple digits there. We're going to keep that 1.720. And this is moles of hydrogen. So now we have moles of carbon and we have moles of hydrogen, and that's real convenient because now we're able to compare the two and kind of give ourselves an idea of how we're going to answer this problem. So let's move this over here so we can get ourselves some extra room. And so what we have here is moles of carbon and moles of hydrogen. I'm going to choose a different color to finish working this out. So what we do here is this is a ratio. There are 0.6880 moles of carbon for every 1.720 moles of hydrogen. And if we were to write this ratio out, it would, look like this. So we have 1.6880 moles of carbon to 1.720 moles of hydrogen. But the only problem is for our formula back over here, CXHY, this isn't a very convenient ratio. Because the ratios in a formula like a hydrocarbon are supposed to be whole numbers. And so we kind of have to use a little bit of I wouldn't say math tricks, but we just use some simple division here to get these into whole numbers. So one sure way to make sure that we have at least one whole number is to pick the smallest one, and in this case 0.6880, and divide it by itself, 0.6880. And in doing that, we get the whole number 1. Now if we divide the moles of carbon, the smaller number here, by itself, then we must also divide this one by the smallest number, so that we can kind of, I guess you would say, reset this ratio to at least 1 to some number of moles of hydrogen. And so we grab our calculator here. We'll move it over here where we can see our work and clear that out. And we have 1.720 moles of hydrogen, and we're going to divide that by the moles of carbon. Okay, we're going to divide that and see what our ratio is. 2.5. Okay, so let's go back here and we get 2.5. So this is much better. It's not quite great yet, but it is much better. If we were to rewrite this ratio up here of moles of carbon to moles of hydrogen, this ratio is a lot nicer looking. So we have 1 mole of carbon for every 2.5 moles of hydrogen in this formula, CXHY. But it's still not quite good enough because we're not really supposed to have fractions like a half in our subscripts. And so what we have to do now, if we still don't have whole numbers, what we have to do now is multiply these numbers by whatever whatever whole number will give us a whole number ratio here. So if we have a half, by multiplying it by 2, we get a whole number 5. And so if we multiply this one by 2 to make sure that this ratio stays the same, we multiply this one by 2. And now, finally, we have some whole numbers, 2 and 5. So there are 2 carbon atoms for every 5 hydrogen atoms. And so that's something that can fit here, 2 and 5. That lowest whole number ratio is our empirical formula. So the empirical formula is C2H5. Now the final thing that the question asked, and let's go back up here to the question and check it. The final thing the question asked us to do is to calculate the molecular formula for butane and then write and balance the chemical equation. So what we have here, is the empirical formula. It's the lowest whole number ratio. It's not really what butane is. It's just what the lowest whole number ratio of atoms in butane is. And so I'm going to erase a little space right here for us to work. because the last step to get to the molecular formula really isn't hard at all. The molecular formula is some whole number multiple of our empirical formula, and that could include 1. We may find that the molecular formula is the same as the empirical formula, but if it is not the same, it is some whole number multiple of the empirical formula. And so the way that we figure this out is we go back to our problem. We look up here. Actually, I believe I'm going to clear out all my math here. Just clear this out. Okay, let's rewrite the important information here. We have CxHy plus O2 gave us CO2 and water. And we have calculated the empirical formula as being C2H5. Now, if we come up here to the problem as it was presented to us, we see that the molar mass of butane is 58.11 grams per mole. So 58.11 grams per mole represents all of the atoms of carbon and hydrogen added together in whatever butane is. We don't know yet. Remember, we just have the empirical formula. So to find out what whole number multiple that we need to multiply our empirical formula by, we are going to divide the molar mass of the molecular formula, 58.11, and that was given to us in the problem, by the molar mass of the empirical formula. Now that's something that off to the side we kind of have to calculate ourselves. So let's go back over here to our periodic table, and we see that one carbon atom is 12.01, and we have 2 of them. So 2 times 12.01 plus a hydrogen. Oh, gotta scroll over here to our hydrogens. Sorry for just a second. Our hydrogen, which is 1.01. So we come back over here, and our hydrogen is 1.01, and we have 5 of them. So 5 times 1.01. So this is our hydrogen, and this over here is our carbon. So the molar mass of our empirical formula is, this is 24.02 plus 5.05. So our grand total is 29.07. 29.07 grams per mole. Now, do this division here, and I'm going to go ahead and pull out the calculator to show you our answer. But I think if you know you're supposed to get a whole number multiple, you can probably see what this is going to turn out to be. So we have, gotta turn it on again. Well, there we go. We have 58.11, oops, one too many, divided by 29.07. And our answer is 1.9989. That is really, really close to 2. And so we're going to go ahead and just say that that is 2. And the reason we're allowed to kind of fudge those numbers and just call it 2 is because we've done a lot of rounding since we started this problem. And so it's likely that these masses are off just a little bit. But basically, the molecular formula is twice the empirical formula. So our molecular formula, we'll just write that down here. Our molecular formula is twice the empirical. So in the empirical formula, we had 2 carbons, so in the molecular, we will have 4. In the empirical formula, we had 5 hydrogens, so in the molecular, we will have 10. This is the molecular formula for butane. It is what butane is. Specifies the actual number of atoms in butane. And so the last thing that our question asked us to do is go back and balance the equation. And so now we know what x and y are. They are 4 and 10. We have 4 carbons and 10 hydrogens. And now all we have left to do is balance our equation. So with combustion reactions, kind of the good way to start this is to balance our carbons and hydrogens first. Our oxygens are in more than one location, and they're kind of best if you save them for last. So we'll put a 4 here to balance 4 carbons in our products to match our 4 in butane. And we'll put a 5 in front of water because 2 times 5 is 10, and that matches the number of hydrogens in our butane. And so now we take account of how many oxygens we have. 2 times 4 oxygens, we have 8 oxygens here. And we have 5 waters, and there's 1 oxygen per water, so we have 5 oxygens here for a total of 13 oxygens. So we use a little bit of a fraction here to balance equations. If you need some practice balancing equations, you can always go back and check out some other videos and practicing balancing equation. But basically what we're going to need here is 13 halves O2. If we had 13 halves O2, we would have 13 oxygens. But since we can't leave this improper fraction here as a coefficient, we must multiply every coefficient by 2 because that's what's going to get rid of this denominator. So the 1, which is not written right here but is implied, becomes 2. This 13 over 2, the denominator is eliminated by multiplying by 2, so we have 13. The 4 is doubled to an 8, and the 5 is doubled to a 10. And you can go back through there and count all your atoms, and you'll see that this is correctly balanced. So that's how you go from masses of CO2 and H2O to calculate the empirical formula and the molecular formula if you're given the molar mass of the molecular formula, and then writing and balancing the equation.